4, fees. Fees are just so interesting. I just love this section so much. I'm sure a lot of people will think it's complicated or boring, but I just think it's the best. So fees are important because they lead to security. And so we don't want fees to fall as a result of the introduction of sidechains, so we have to discuss it. Again, we're talking about going beyond these limits here. And I'm going to spend 4 slides on review assumptions and kind of framing this discussion. And then I'm going to discuss 3 different perspectives on how a sidechain future might play out, drawing on existing commentary about block size, etc. Then I'm going to talk about Bitcoin's transition to equilibrium, which is something that everyone knows about, but I'm just going to remind everyone. And now then in this part 3 of this section, I'm going to talk about the market for block access, which I think is just a fascinating topic. In parts 4 and 5, I'm going to take what I believe about the market and use it to make predictions about what will happen. So this is a very old topic. Let me begin by saying this section is very narrowly focused on transaction fees. It's not focused on anything else. It's not focused on what the block size should be. I think that's mostly an externality question, and I've written a lot about that already, and there's lots of ways of solving that and managing that. This is narrowly only about fees. Nonetheless, we will be framing this discussion as if it removes Bitcoin's block size, and I'm going to explain that on the very next slide. But I just wanted to bring up, this is something from 2013, a sort of battle between Mike Hearn and Peter Todd. It went on for a while. It went on to a different thread. Peter Todd has some points here that I'm going to return to later, which I think are just perfect. Without the block limit, we can expect transaction fees to fall to the marginal costs of a transaction, which means the fees aren't paying for any security at all. This is because the marginal cost of a transaction is effectively 0. It's a digital good, and by the time the miner hears about the transaction, it has been sent to them over the internet already. So we're going to talk in tremendous detail about this, but it's effectively free now for the miner to include this transaction. There is a storage cost, which is why miners would not be able to create like a 10 terabyte block. So, but ignoring these small costs, it's effectively free, which is why he says that fees aren't paying for any security at all. That's one extreme. And on the other hand, with a small block size limit, as Peter Todd, have been arguing for, you run the risk so few transactions, the quantity of transactions, so few transactions actually happen on chain that security still isn't being paid for. So fees may be high, but the quantity may be low. And we're going to be talking all about this in this section. So first I'm going to make my worst case assumptions, which are that someone creates a sidechain of Bitcoin with all the economically relevant limits removed, and that it makes it into the system so users agree to run it and miners agree to run it. And furthermore, finally, the sidechain transactions are perceived as perfect substitutes for Bitcoin transactions. Now, I think this is very unlikely, but nonetheless, this is what the assumption we'll be using. So a user is indifferent. Should they get it into the main chain, or should they get it into any number of these weird sidechains? Any number of these weird sidechains. And to make it simple, I just say we've got one sidechain with effectively not an infinite limit, but like a 100 gigabyte block limit or something that's effectively unlimited. And in doing so, it's effectively removed Bitcoin's limits because it's now in competition, direct competition with something that has no limits. So the total space is unlimited. Now again, you as a node user are not directly affected, but you are indirectly affected through your mining experience should security fail, which is this next point. Fees equal security. The total fees paid in a block, or even in a set of blocks, determines the denial of service attack cost for that section of the chain. If you can pay the total sum of all the fees, you can fill up the blocks with your own garbage and stop anyone else from using the blocks. Now, people can outbid you on an individual basis, so it's slightly more complicated than that. But what's less complicated is that the cost of rewriting the chain is by definition equal to the value of the subsidy plus the sum of the fees for each block that you, so the sum of this across all the blocks that you want to rewrite. And this is because all of that money is being released to miners to compensate them for finding the block. And since this is an anyone can join super competitive market, people will join and expend resources until the total expenditure by everyone equals this revenue. Everything that has been spent on mining will equal everything that is earned by mining. So none of this is any news to anyone. I just bring up this because once a predetermined number of coins have entered circulation, the incentive can transition entirely to transaction fees. So eventually the rewrite cost will only be the sum of the fees, which is why fees are very important. Now, again, I don't really believe that thing that I just assumed, so I just want to point this out. Instead, I think a sidechain will probably do something that Bitcoin can't do, so people literally won't be able to use them as substitutes. It'll be literally impossible. So in these cases, the chains don't affect each other, but total security, i.e. total hash rate, is actually pooled because it's the same miners mining all the chains, so more transaction fees, which means more security for us. And even better, it's possible that some sidechains might draw everyone into the Bitcoin family and spread the gospel of Bitcoin, in which case a transaction on a sidechain makes it more likely that someone will also need to transact on the main chain, which is extra good for us. Okay, so with that out of the way, we're going to really dive into it now. More or less the picture today. This axis is quantity. As I'm going to explain on the next slide, it can be anything, but right now it's going to be kilobytes. And this is the price, aka the transaction fee rate, in terms of Bitcoin per kilobyte. Here I agree with Peter Todd's implied point that the marginal cost of including the transaction is 0, because by the time you hear about it, it doesn't really cost you anything to include in a block. And we are going to talk about that in more detail later. This is the demand curve for Bitcoin transactions. The more the gospel of Bitcoin is spread, the further to the right this moves. And then we have a vertical supply limit here. These intersect. This is some rate. Individuals try to pay fees that are as low as possible, but if they pay too low, they'll be outbid by someone else. Long story short, this is the effective Bitcoin per kilobyte fee, and this is the total number of kilobytes, which is our infamous 1 megabyte block size limit, and then you multiply those and get the fees in the block. So this is a diagram that we'll see a lot of. And the interesting thing is this doesn't matter, this quantity axis. It could be several metrics at once or one composite metric. I know that for the deployment of SegWit, there's now something called weight, which is kind of just a mixture of different kilobytes. Not going into too much detail on that, but this could be SigOps, signature operations, which are expensive because CPUs need to perform them, and there's not an infinite amount of CPU resources. So this could be anything or a composite, so I just want to explain that. So now with that graph in mind, there are these three perspectives about what would happen if we took this limit here, which I've kind of made transparent, blue transparent limit, and we removed it. This is Peter Todd's first view, which I'm going to call the tragic view. We could call it the anarchist view. It's unmanaged by anyone. Here, the miner who charges the lowest fee eventually collects all of the transactions into their block. So you just a little bit of patience, and everyone sneaks in at the lowest possible value. And since failure to maintain a high price is inevitable, all the miners charge a low price, and we are in this situation here. I'm going to talk a lot about that in the future. This is a market view, which states that the supply curve is in fact upward sloping. So far, the only person to take this view has argued that this is due to orphaning, which we are going to talk about. Then this is my view here, which is actually that the miners will form a cartel for the explicit purpose of maximizing transaction fees and doing nothing else. So you could call this the managed view or the gouging view, and I'm going to talk about why I call it that in a moment. First, I'll just say that these views have a completely different shape for their supply curve. So these perspectives are quite different, and as a result, they reach opposite conclusions. Here, transaction fees are minimized at 0. Here, there's some quantity, ambiguous quantity of transaction fees, and in this view here, the transaction fees are actually maximized. They're not only healthy, but they're maximized. The three perspectives obviously come with three different predictions. So the tragic view says that the system will crash. The market view says the system doesn't require any management and should be unmanaged. And this view, the cartel view, claims that management will maximize revenue. It doesn't claim that we should or shouldn't, it just claims that it will maximize revenue, and it will therefore exist. Section 2 of 5, transitioning to equilibrium. The early days of Bitcoin are not representative of the steady state, and I think everyone knows that. Incentive to transition, it's quite clear. In Bitcoin's first 4 years, the block subsidy was 50 Bitcoin per block. And over that time, the average total of transaction fees in a block was 0.04 per block. So each of these 3 stages is in a per block world. This gets cut in half every 4 years, from 50 to 25 to 12.5. This has been increasing by roughly a factor of 5 every 4 years, and it is in fact accelerating. I noticed that it was up by a factor of 6 over the last 2 years. Instead of being up by a factor of 5 over 4 years, it's up over a factor of 6 over 2 years, so it's actually accelerating rapidly. As a result of this, miners will treasure blocks for their fees. They won't necessarily treasure finding a block. They'll be happy to find transactions that have fees, really. So this will be slightly different. And what I'm going to call a growth attitude will diminish in favor of a new adversarial attitude. So miners were playing nice while the system was young because they got paid 50 Bitcoin and they wanted the Bitcoin to be valuable. But I think in the future that will change. When they're not paid Bitcoin at all, it'll just be the transaction fees that they charge users. Users will want those transaction fees to be low, but miners will want them to be high, so there'll be some tension there. Finally, demand for Bitcoin will increase and change. So a hobbyist would need low fees to toy around with this. That was sort of the original phase. We're kind of now in a black market, gray market kind of phase, perhaps, where Bitcoin is often used for extremely private transactions. And we may reach a point where everything from your salary to your supermarket is within a Bitcoin network. And at that point, you won't need an inducement in the form of low fees to join the network. It'll just be your network, and that's what you're on. So how different will it be? It'll be pretty different. Miners will engage in fee maximization because, again, the thing that really will care about in steady state is the fees. And users will then counter that by engaging in fee minimization, which is why this line is flat. So the question is, to what extent can miners fee maximize? And I think they'll succeed completely. But in order to get there, we're going to need to talk about the market for block access. In order to do that, I am going to talk a little bit about a normal market. And I hope it's not too patronizing, but I think it'll be clear once I talk about this that there are actually some very interesting abnormalities in our case. And these have tremendous implications. Finally, I'm going to talk about something called the block tree. So this is a sub-agenda. Point 3 is so involved, 15 slides, that it has its own agenda. Again, this is my view here. This demand curve is produced by people who want to broadcast messages. They want to broadcast a message that is 2 kilobytes more than they want the transaction fees associated with sending that message. So if a Bitcoin transaction is 2 kilobytes, they value the ability to broadcast that 2 kilobyte message in the blockchain more than they value the transaction fees they pay, 0.01 for example, more than they value the 0.01 Bitcoin transaction fees that they pay. That's what produces this demand curve. We're going to have a limit here in the future per single block. It's going to be more complicated across many blocks and across different chains. But that preview aside, I do want to take a moment to talk about a very normal market, oil. And so we're going to build the demand curve first as a sort of warm-up, and then we're going to do the supply curve. So we have our classic axes, quantity in gallons, price in dollars per gallon. Just an example. Now the demand curve is produced by each individual person's willingness to pay for oil. They value oil more than they value $10,000. It's hard to measure, sometimes it's impossible. But it always slopes down because it's sorted from highest to lowest. So there's no funny business there. It's by definition it slopes down. And here I've constructed some examples of maybe the first 5 people who really need oil. And so, for example, this individual needs 10 gallons of oil, and he'll pay 10 grand per gallon. Now, who might pay such a thing? Well, hypothetically, if someone was throwing a fundraiser in Manhattan, New York in the winter, and it was a billionaire fundraiser, and he's a billionaire, and all of his friends are billionaires, and it's going to be really annoying if it's cold there, then, and this guy runs out of oil, and he might, if he absolutely had to, which he will not have to, but if he absolutely did have to, he would pay 10 grand for 10 gallons of oil each. So that would be $100,000 to heat his place for the duration of his fundraiser. And this individual green character, going from 20 to 1020, he needs 1,000 gallons of oil, and he'll pay 4,000 per gallon. So this project right here is worth $4 million to him. Perhaps this is another super wealthy individual who needs jet fuel to fly and visit a sick relative or something on their deathbed or what have you. This is the meat of the demand curve, and if you zoom out, it just tends to look like this. It's not a straight line because that would imply that each delta is the same. In other words, each gallon of oil is worth exactly some amount less than the gallon of oil which preceded it, which is highly unlikely. For example, this individual here, probably it's not even flat for him. It's probably curved. He probably wants to heat up the first gallon of oil is worth more to this individual than the second. He really wants to heat the fundraiser room up from 45 to like 60 degrees during the most crucial 2 hours, which might only take 1 gallon of oil. But more than that, he'd prefer to like have the entire place be very warm, 72 degrees for the duration of the event. But the first gallon is worth the most, and after that the gains decline, so hence this shape. Now the supply curve is normally the same for a good that already exists. But for a good that does not exist and has to be produced, I'm going to walk through a different way of building a supply curve. So again, for oil, there are different ways of making oil and different projects that would produce an amount of oil. So let's say you want to use land site 2. You may need to pay a huge amount up front. And I would take this giant amount up front and I would divide it by quantity. I'd spread it over this quantity axis and produce a rectangle here. And then this amount would be what's called the average fixed costs, what an accountant might call selling general and administrative. The capital costs, and then this triangle here would be the variable costs, what an accountant might call operating costs or costs of goods sold. So these are costs that you need to pay per gallon of oil extracted. And if you extract them all, then you get this kind of trapezoid shape. And you've paid this kind of trapezoid shape, and this is the cost of supplying oil. So if oil comes in, in economics, the graphs actually run independent variable in from the side and then dependent variable vertically. If the price is some certain amount, you'll engage in this productive activity. And then you sum these horizontally. So you take the cheapest production method first, until you've produced all the oil you can and using that method, and then you switch to the new production method. And then now here you're kind of going back and forth between two, so that you can always make the cheapest oil you can make. So which is why this gray line is beneath my projection of this purple line. And this forms a kind of supply curve for a good that's produced, like oil. These curves intersect at some point. This produces a market price and a market quantity. All this oil is produced at some cost, and it's all sold at some price. This triangular region represents happiness. This triangular region represents profit going to producers, ignoring Parisian rent, which we don't have time to explain. That's a normal market. Now, the normal market has, I hope that wasn't too boring, a normal market has certain features, namely the interaction between two sovereign decision makers and their conducting of a unique transaction. So you can look at what's happening at the margin here. We have two suppliers. One will sell a barrel of oil for $3. The other might sell a barrel of oil for $3.2. And the customer buys the cheaper barrel of oil. You might call this rivalry. This guy makes a sale. This guy goes home empty-handed. This guy gets his oil. Orange guy. And on the reverse, you could have one individual be willing to pay $3 for a barrel of oil, and another individual only be willing to pay $2.9 for a barrel of oil. This guy makes a sale. This guy gets his oil. This guy goes home empty-handed. Now, these features are not present in the market for block access. This fundamental idea of quantity of things being produced and then having them be traded between one supplier and one consumer does not exist in this world. Buyers don't choose their miners. So you just broadcast your transaction out into the world. Now you may pay only a $3, for example, transaction fee, and it might only be picked up by this miner, but you don't choose to go with one miner over another miner. You just broadcast the transaction out. And in fact, the idea of two sovereign decision makers doesn't make any sense because there's no concept of an individual either. So there's not necessarily any relationship between an account, a cryptographic account, and an actual agent who makes decisions. So one user can have many accounts for a start, and one account can even have many users, as was the case with multisig, and miners can be in pools, and pools can have administrators. And we'll get right back to this. I have two more that I want to bring up. First, another interesting abnormality is that miners do not control their own block production. This is very different from like the oil example where you could ramp up production if the demand were there. But in this case, you can't choose to make more blocks. And such a choice doesn't really make any sense because each block can theoretically, not in practice, but in theory, could hold an infinite number of transactions because the work is done on headers, and headers only contain one little hash of the Merkle tree of transactions, and that item is the same size no matter how many transactions are fit into the tree. But here, most interestingly of all, sellers have nothing to sell. Unlike someone who has a barrel of oil, they actually have produced a barrel of oil and it is now an asset that they can, one oil barrel that they can sell or not sell. But in Bitcoin, before the block is found, a miner can't guarantee that they will find one. And I mean this both literally and practically. So literally, it is statistically, there is some likelihood that they will never find another block. It's obviously vanishingly small over a certain time period depending on hash rate, but it is possible that they'll never find a block again. But I'm more emphasize the fact that in practice, you can't go up to a miner and tip them $20 in US dollar cash and say, make sure that you get this into a block, because the miner can't guarantee that. But then, post-block, it's too late to change your include-exclude policy. So whether or not the transaction was included or in a block or not, once the block is found, this information is all fixed and immutable. So this is quite interesting. So now let's return to those two that I first mentioned of the four. So there's no price competition among individual miners. Instead, what there's no concept of an individual really at all. And instead, there's just a gigantic shared customer pool and a shared production schedule. So we have this very big kind of aggregation on both sides. A giant pool of customers that all the suppliers know about, and the same production schedule that all the consumers have to put up with. So it's very kind of some interesting tension here, which we'll explore. What's the implication of this? Sellers don't control block production. Well, I think this one's quite clear. Blocks are not the relevant thing supplied. It's the transaction space. The blocks are kind of more like a clock. It's really just the distributed timestamp server concept from the Satoshi white paper. Now, what about this one here? This is the one that I think is most puzzling and interesting of all. Not only do users and miners never talk to each other nor interact with each other, there's nothing a miner really could say to an individual. Their proof is when they find the block, that they included your transaction and that they did the hash rate. So in my opinion, sellers, aka miners, have nothing to sell to Bitcoin users. Miners are not transacting with Bitcoin users, but this of course begs the question, who are they transacting with? It seems that there's only users and miners and no one else. So what exactly is going on here? In my view, there is an intermediary in between miners and users, which I'm going to call the protocol. Miners don't work for users, they work for the protocol. And their contract is renegotiated every 2 weeks as the difficulty adjusts. And these are contractors who work for Bitcoin. They supply hashes, hashing activity, as well as an access policy. And in return for supplying these two things to the protocol pays them Bitcoin. What is an access policy, you ask? Well, it's something that takes features of potential transactions, which are zero confirmation transactions. It takes their features, such as the fees paid, the kilobytes of the transaction, the SIG-ops, and potentially anything you would like, and it maps that into a include in a block or do not include in a block decision. So miners supply immutability and they supply spam control. And since anyone can join, as I rambled about in part 2 of this giant talk, anyone can join at any time and provide these items. There's brutal competition for this job. Ultimately, the suppliers would compete down to something like subsistence wages, in theory. On the other edge, we have the users, and in my opinion, users have an ability to convert their Bitcoin into fees. So if they want to broadcast a message, a 2,000 kilobyte message, and they care more about broadcasting that message than they do about owning 0.03 Bitcoin, they can create a bundle, which I'm going to call a prospective transaction, which contains the message and the fee. And it will be broadcast around. These prospective transactions are always zero confirmations, and they do differ as a function of each access policy on how likely they are to be placed in a block. And then between these two, the protocol sits in the middle, and every 10 minutes it does something interesting, and I'm going to zoom in on this. So this is what I call the block tree, and it helps me think about these issues. So in my view, you start now, and then now plus 10 minutes, give or take, and then now plus 20 minutes, give or take. And this is where we are at the present moment. And then each of these arms is a unique access policy. And these access policies are weighted by hash rate, the hash rate of the miners subscribing to such a policy. So maybe 11 small miners support this branch. It sums to 40% of the entire network, indicating a 40% likelihood of traveling down this path. Maybe one giant miner follows this policy, and he could have 35% of the hash rate all by himself, indicating a 35% chance of traveling down this path. And the remaining 25% could maybe be 2 miners or 100 miners, it doesn't matter. So this concept of the block tree, it's only to help me think about this market for block access. So it's fully defined as a concept. It's not necessary to write out the entire tree because that would be gigantic. And the whole point of it is just to help me think about what's going on. And the reason it's helpful for me is that it's clear that each miner has a monopoly on their block in the tree. But a miner can't force their block to become part of Bitcoin. That happens randomly according to the laws of statistics. And the insights I draw from this are that this right here is not a market process at all. Instead, it's what I'm going to call a serial monopoly. It's just a set of monopolies in a row. However, the situation with hash rate is quite the reverse. Anyone can join at any time, and each hash has an equal probability of winning. So we have an incredible dichotomy here between perfect competition and monopoly. It's a classic dichotomy in economics. The dichotomy is basically that the monopolist chooses not only how much he makes, but how much everyone makes, because he equals everyone. It's just him. The perfect competitor, if he cuts back, other people ramp up, and if he ramps up, other people cut back. So he's irrelevant. This person has been defeated before they even begin as far as strategic quantity is concerned, whereas the monopolist has an interesting decision to make, and we'll talk about that. An interesting thing is also that even though this is a serial monopoly, the monopolies might compete with each other over time, which is what we're going to talk about in precisely 3 slides. So I think with this concept of splitting this into thirds, it's a little bit easier for me to understand what's going on. The protocol offers a fixed contract that's renegotiated every 2 weeks, and you can join or leave that contract at any time. And on this edge, we have a service where anyone can convert their Bitcoin into fees for potential transactions at any time. So we have totally unrestricted entry and exit on these edges. But in this middle part, we have like a monopoly tree, and that's really bizarre. Let me just remind you where we are. We're about halfway through this fees section of the presentation, part 4. And this section had its own section, so I got kind of big. And now we're going to talk about how miners can and might react to such a market. In general, we have this dichotomy here, and Ronald Coase, a great economist, is going to be on this side, and there's something called the Folk theorem that will be on this side. This is Nassim Taleb talking about how awesome Ronald Coase is. He's really is an awesome guy. He died recently. I think he was like 102 years old or something. Anyway, Coase has a conjecture that says monopolies lose if customers are patient. So I was saying the block tree that competes with itself across different time periods, that is exactly what this is. An informal argument that durable goods monopolists do not have market power because they are unable to commit to not lowering their prices in future periods. Because the monopoly is, in effect, in price competition with itself over several periods, and the customer with the highest valuation, if he is patient enough, can simply wait for the lowest price, the monopolist will have to offer a competitive price in the first period, which will be low. And I've tried to explain that on this slide. This is the tragic Peter Todd view, and I've explained that if these individuals are patient, they can just wait for one miner with an unconstrained limit to grab all these sales, and they get all the transaction fees that are all low. They get all of them, so they get like 1,000,000 times epsilon. And since such an individual exists, all of these individuals who are getting 0 sales have an incentive to switch to this, such that even in the very first period, everyone will be tragic. So these will all become tragic. In the other corner, we have the Folk theorem. The Folk theorem, I think, will defeat the Coase conjecture. I'm going to talk about why. Because they are unable to commit to not lowering their prices in future periods. Well, what I'm going to argue is that using the Folk theorem, they can, in fact, commit to doing this. What is the Folk theorem, you ask? Well, it's one of the most important things. I think it's tremendously related to mining strategy, so I hope you'll indulge me as I explain it. The easiest way to explain the Folk theorem, as it's almost always explained, is with a repeated prisoner's dilemma. So the prisoner's dilemma is where two individuals can either cooperate or defect. If they both cooperate, they benefit. They get 2 points each. If they both defect, they kind of do worse. They only get 1 point each. So you'd think that they would both cooperate, but the problem is if one of them cooperates and the other one defects, then you are screwed. 0. To make matters worse, they have an incentive to screw you over. They move from 2 to 3. That's the prisoner's dilemma. We're going to transpose it into this diagram here. This is red. As red does better, red the row player. As red does better, we move to the right. And this is blue. As blue does better, we move up. So you can see that defect is more to the right for red than cooperate is. In fact, within each decision that blue could make, red is always moving to the right. Red is always gaining by defecting. Similarly, blue, the defect is always above the cooperate, and even each of the points is always higher. Hence, both will defect, and the only place where defect and defect overlap is right here, which is the payoff of 1, 1, which corresponds to this value here, 1, 1. If red cooperates and blue defects, red will cooperate with a C here, blue defects. You can see we've reached the top. Blue is very happy. He's reached his highest point. Red is very unhappy. He's most to the left. He doesn't like that. Now the Folk theorem says that, believe it or not, if the game is long and players are patient, then it's possible to punish players. You can punish them in the future for miscooperating today. And since you can do that, the ability to punish ensures cooperation. And since you have this ability to force people to cooperate, mutually, all the players can hit any region that's better than what I'm going to call the punish equilibrium, which in this case is this. Punish equilibrium is when one player acts such that the other player is unhappy. In this case, defect. So, since this is the punishment equilibrium, they can hit anything above or to the right of this together. And how do they do that? Well, you just choose whatever you want in this green region. And then you play that until someone doesn't play it. Because this equilibrium is determined by both an x coordinate and a y coordinate. So you just say, okay, I'm gonna play this, and if someone else doesn't play that, I'm gonna punish them in the future to erase their gains. So that's one insight, that if punishment is possible, cooperation is enforceable. The other insight is that if value transfers are possible, then the total cooperative value is maximized. So I've added these little negative slope 1 lines. Normally game theory has these units of utility, and utility is ordinal, which means that it's just in order, first, second, third, fourth, fifth place. But if instead you're measuring the payoffs in actual money, then it'll always be possible to transfer some money from one player to another. Whether or not anyone would want to do this is a different story, but it'll always be possible. And as a result, you won't ever truly be in equilibrium until you reach this tangent point. Because if you're not at the tangent point, say you're somewhere on this line, blue can offer red a deal. Blue can say, look, let's move up from being on this lower line to this upper line. I'll gain a bunch, and then I'll transfer some of that back to you. 5%, 50%. 3%, whatever. And so it's never in equilibrium until you've moved up as much as you can. So applying this to fees, I think we'll be able to enforce a rule that maximizes fees, which I'm going to explain in section 5. And therefore we won't actually be in equilibrium until all the miners are agreeing to maximize those fees. They'll have a rule for maximizing fees, and if you don't follow that rule, you'll be punished. And in this case, we can punish very easily by simply orphaning the block. So we have this cartel view that I think will win, and as long as there's tractable rule here for ignoring misbehaving individuals, it's not the case that all sales go here, and it's not the case that 0 sales go here. So perfect competition, instead of winning, it actually loses, and we have a monopoly. We have a monopoly on the access policy. It's a coordinated single monopoly because we actually were able to commit to not lowering prices in future periods. Now we need a rule for excluding certain blocks, which I'm going to call a revenue fork. So it's kind of a weird soft fork. So typically soft forks are used to upgrade Bitcoin software, but I'm not saying that we should. I'm not saying that it should happen. I'm saying it will happen. So I'm saying we will see some fork to manage the business policy of Bitcoin, specifically to optimize transaction fees. And someone will come up with such a rule, and anyone who doesn't follow the rule will be orphaned. And now I'm going to explain in section 5 what such a rule might be. Okay, so in section 3, I described some unique tree of all the different access policy combinations. But in section 4, I advocated that miners would actually be able to trim the tree and focus in on a single access policy and hold that access policy across time. So I'm giving it to the monopoly perspective in sections 3 and 4. All we need in order to do that is a predefined software rule that maximizes fees, which I'm now going to talk about. So since Monopoly 1, the monopolist, as you may know, the supply curve normally answers a question, if the price were X value, how much would be produced? But the monopolist just chooses how much he produces and how much he sells everything for. If the monopolist doesn't choose a point on the demand curve, he loses money. So effectively, the miner is picking a point on the demand curve. And I have a simplifying assumption here about demand. It's really not a big deal, but I just assume that demand is constant within a 1-week period, so it doesn't deviate a lot within a day, or like when the sun is over the Pacific. So I try to approximate a future where there's a constant backlog of transactions, so like the Lightning Network type future. So in order to construct our rule, we need to figure out where revenues are maximized, or we at least need to take a decent stab at it. So total revenues, again, is this field multiplied by this field. And we are now going to come back to Peter Todd's excellent comments from 2013, where he explains that without the block limit, we can expect transaction fees to fall. No security, that's this view here. No limit, high quantity, fees priced very low. And on the other hand, you run the risk that so few transactions actually happen on chain that security still isn't being paid for. That's this extreme. This is sort of where we are now. It's good for externalities, but it's bad for fees. On this extreme, over on the right, we have something that's bad for externalities and bad for fees. So this one's very bad. And then in the middle here, we have something that's kind of medium for externalities and good for fees. So for externalities, it goes good, medium, bad. And for fees, it goes bad, good, bad. So we want, because this section, again, is narrowly focused only on fees. I hate to be misunderstood on this point. Miners want a medium limit as far as fees are concerned. And what I'd like to contribute to the conversation is that demand is the trade-off as we move from here to here. It's demand that's the trade-off. It's basic calculus that if demand curve were a negative 45-degree line, a square would maximize the area. It's also extremely basic calculus that if the demand curve is any downward sloping line, we can easily calculate which Q would maximize the total fees. It's maybe freshman year calculus that if we have a parabola, which the demand curve is almost always a sort of sloped curved shape. So if we define a parabola that has a positive A, negative B, so that it's like a U shape, and then we define the demand curve as the left half of that, then we can do some classic optimization stuff and calculate X star, the quantity that maximizes the revenue there. But the issue is that tricky shapes are possible. So we could have what I'm going to call a decoy parabola, like maybe you're trying to estimate a parabola shape and you come up with this, and do you calculate your square? Shape is this green thing, but you are tricked, right? If you had just come in a little bit, moved a little bit to the left here, you could have picked up all this extra area. And you might have other problems, and then on the right here you've got a decoy local maximum. So this sort of looks like if you looked around from here you'd think you were at the maximum, but if you jumped all the way over here you'd see that actually this was the maximum. So this is kind of annoying. So what I propose, and this is just a very first draft of such a thing, and this could be improved by someone probably, is we take a very simple greedy rule. We adjust Q by some percent, 1% for example, and then we measure P's response. And this is wonderful because Q and P are very easy. The software is already aware of what they both are. And without getting bogged down by the details, if the area increases, you keep going, and if the area decreases, you reverse course and go the other direction. And as such, you will grow into, you'll move around and find, and then you'll be trapped in a little spiral at the local maximum here. Now, it's a very simple rule. We could enhance it in many ways. You could change the jump magnitude. So if you moved a little bit in some direction and that paid off big, then maybe you want to really jump very far in that direction on your second move. We could incorporate all kinds of averaging, similar to the difficulty adjustment. We could say average, we could build this up over 2 weeks and then change it for a 2-week period, or a 2-month period, or a 2-day period, it doesn't matter. And then we have this idea of a subjective minor leap. So if you think you might be trapped in a local minimum, this entire thing, this revenue fork, is purely to benefit the miners and get them more transaction revenue. And so if they want to all contact each other and try and leap from here to there, because they think that that will increase revenues, they're welcome to attempt that. And finally, we could have some kind of tolerance, like there could be a hard Q limit, but you might be able to keep it within some range or something like that. There are all kinds of different modifications one could make. I have a note here. Even though Q is fixed and globally coordinated by a mining cartel, the individual transaction selection is not. And so the miners still compete with each other on who includes which transactions. I think the more important thing, if you're concerned about miners acting as a giant group to censor transactions, The more important thing is, I think, to just work on things like Lightning Network and transaction fungibility, confidential transactions, etc. I think that's the area you should go. I wouldn't fight this. So I did all that work, first because it was so much fun and I just love talking about markets and such. Even though it's a little depressing, I think I started at 3 or 4 and now the sun is setting. But the question we were trying to answer was, can revenues fall if Q is controlled by miners? Because revenues determine the security. And it seems to me the answer is no. In fact, miners are willing and able to vary Q such that revenues are maximized. So if anything, the revenues would increase in this narrow context of the fees. Fees only. This is not about block size. My conclusion, from a fee perspective, it is safe to allow miners to use sidechains to increase Q. And I think it's even safer, again, if the sidechains have a distinct purpose. There's way more to say about this, but that's enough for today. Now, finally, we've reached the end. The sun is setting, which is surprising to me. I guess the day really flew by.